Class, I'm recording this lecture of today. So let me go back to my screen. Okay, so let us have a recap back what we have learned. Okay, last week. So first of all, we have learned on how to classify either this is the structure is stable or unstable. Then we classify on either this is a determinate, statically determinate, or indeterminate. From here, we actually use equation to determine the degree of indeterminacy. Okay, we have two equations here. Anyone can help me for the beam and for the truss? What is the equation that we use for the beam? Can anyone help on this?
R minus E minus C.
E equal to
Oops. Okay. Mm. Okay, maybe I will just write again. What is the D? Okay, D is the, for the beam, just now I have heard you are helping me. R minus N minus C. So the R is the support reaction. The N is always 3 for 2D structure. And the C is the hinge, the interior or internal hinge. And may I have this D equation for truss?
M
M
plus R
plus R.
minus 2J.
Thank you. So M is the member, R is the reaction, and J is the joint. Okay, so before you analyze your structure, either beam, frame, truss, composite structure, you need to determine whether this is a determinate or indeterminate structure. Then only you select appropriate method to solve the structure analysis. Okay, so but in this chapter 1, we will deal with the determinate structure. Okay, so but you still need to go through this process. Okay, so this is what we have learned in our last lesson. And then we also learn on the joint method and also section method, okay, to solve the truss analysis. Okay, but I have share with you more example on the using the joint method. Okay, so now we recap back on the this joint method. Okay, so if you have a systems, okay, let's say this is three truss that we have used in our example. Okay, so you first of all you might want to solve for the support reaction. Okay, then we are going to focus on the joint by joint. Okay, what we need to do in the joint method is we want to go to analyze the equilibrium in a joint. You need to observe in this joint A, joint B, or joint C, which joint that you can start with. And please make sure that that particular joint should not have more than 2 unknown forces, because if that is more than that, it will be difficult for you to start with. Okay, few of you actually have contacted me on the tutorial problems, okay, and asked whether how to solve on this problem. Okay, I have also shared with them that if your support reactions, I mean, cannot be found from your equilibrium equation, you can also start, okay, in the joint equilibrium, solving the equilibrium at joint first without solving your support reaction. There is no problem. Okay, so but now the general procedure is we solve the support reaction first, then we go to joint by joint to solve the unknown forces. Okay, let's say once you have identified the nodes, okay, to be proceed in the joint analysis, what you need to do, you need to draw the free body diagram of the joint. Okay, so since we are using joint method, so you need to draw everything. Let's say you pick A. Okay, you have chosen A, so you need to draw all the forces at A. So for example, you have the support reaction AY, you have AX. Okay, if this is already solved, you put in the the correct arrow. And then this is unknown. The tips we have shared earlier is we assume tension for the unknown. Here we have FAB and then we have FAC. So this is your free body diagram, and of course put in any geometry inputs that will be helping you to solve these unknown forces. For example, in this case, you might need the angle theta. Okay, then the second step is to use the equilibrium equation. Okay, just to recap a quick one. So now from here, we need to use the summation Fy equal to 0, summation Fx equal to 0. Since we are practicing taking this joint, choosing the joint, not more than 2 unknown. Okay, the more equations that you are solving is 2 simultaneous equation, or you can directly solve your equations with 1 unknown. Okay, in these equilibrium equations. Okay, this is what you should do in your joint analysis. Okay, so any question here, class?
Good, madam, good.
Okay, so the third one we have learned is we determine the deformation of the joint. Okay, meaning that we are, maybe I need to use a new page. Okay, just a quick one to recap. Okay, so the third one, we determine the deformation or deflection or displacement, okay, of a joint. Okay, a joint. Okay, in our previous example, okay, so just to sketch back again let's say this is the real structure. Okay, okay, we have, let's say we have a vertical loads, okay, 10 kilonewton. Okay, so to solve this one, the deformation of a joint, in our last lecture, we have used virtual work method. Okay, in the virtual work method, okay, first we need to analyze, solve the real structure. The real structure will come from the real problem. Okay, the determinate truss. Okay, we name this a big N. Okay, then we solve all the forces using the joint method. Okay, for all these NAB, let's say, or FAB, and so on. Okay, all these N. Then the next step is we create a virtual structure. Okay, or an imaginary structure. Okay, then we name this as small n. Okay, so let's say we want to find, let's say this is C. We need to determine the horizontal, okay, this displacement at C. So then in this virtual structure, there are 2 characteristics, main one. We can remain all the geometry, there is no problem. Okay, this is what you should do. Then the next thing is we need to remove, or we don't include the actual loading. So the 10 kilonewton should not be included in your virtual structure. Then we add 1 unit force. Okay, where? At where you want to determine at the location and the direction where of point of interest. Okay, I would say. So now what your interest is at C, and it is horizontal. So you place horizontal at C 1 kilonewton. This unit you need to follow exactly in the real structure. Okay, so then you solve for all the these virtual, the axolots in the virtual structure. Then we applied, okay, summation N L over AE, okay, for all, to sum up all these effects from all the members. Of course, you also being exposed on deal with the temperature and deal with the fabrication error. Okay, so please, maybe we can put in the equations here. What is the equation when the truss is deal with this temperature? Summation N alpha delta T L. Okay, so and for the fabrication, we have summation N delta L. Okay, so this one you need to make very clear. Okay, because we are going to use it also in chapter 2. Okay, the similar concept. Okay, do you have any question? If not, I will proceed on today's lecture.
No, madam. Proceed.
No, madam.
Yeah. So now we are going to move on to another type of structure. Okay, of course, we need to make sure this is still determinate system. Okay, so we will analyze the beam, and let's see. Can you see my slide right now? Analysis of beam.
Yes, madam.
So there are few outcomes that we want to achieve from these slides. Okay, but I can show you in this morning is on 1 and 2. Okay, so you can have a reading on 3. I will try to prepare a short video on how on one example on this item 3. Okay, so first of all, you need to be able to determine the reaction of statically determinate beams. Okay, so we need to how we use the equilibrium equation to solve support reaction, and then we determine the shear and moment values. Maybe I will more prefer to say the equations. Okay, equations of shear and also bending moment. Okay, for a statically determinate beams. From the equations, you are able to know exactly the shear and moments values. Okay, at any point. Okay, in your this statically determinate beams. Of course, I will show also in these slides on the shear force and bending moment diagram. Okay, shear force diagram and bending moment diagram. Okay, so there are some reading slides here that you need to go through later. Okay, and then maybe I will stop here and explain a bit on this cut section, the method of cut section. Okay, we have explained the cut section method in truss structure. Similarly, we are going to practice this in our beam. Okay, so what is this cut section method? Is when you have a structure, a beam structure, we are going to cut into two. So the cut section will be depend on where you decide. Okay, so this BB, if you can see that I have putting this B prime. So you can cut before this P kilonewton, the loading, or before is here. Okay, let's say A prime. Okay, cut a section before the P kilonewton or after the P kilonewton. Okay, so but when you have putting a cut section, so this structure become two parts. Okay, so this is a section 1. This is a section 2. Okay, then we need to analyze the equilibrium in one of the section you choose. Okay, to solve for the internal forces. Okay, let's say we cut at the right section. Okay, so meaning that you're going to block everything here. Sorry, it's B prime. So this will not be used. Okay, we are going to focus on this cut section only. So what is missing here? Anything missing for this right section, section 1?
No medium.
This is missing P kilonewton.
Okay.
Yeah, anything on that section, especially the load, the support reaction, okay, or even the section sizes, everything on that particular cut section must be included in your analysis. So if you have my notes right now, please put in this you have a P kilonewton here. Okay, don't miss that. Okay, so of course here you're going to have, oh, I cannot write here, so AX, AY, and also AX. So then you can analyze this section. Okay, how about the other section? If you want to analyze a section 2, okay, then you go back to this BB prime. There is no loading on top of it, but you have a rollers at C. So you need to put in this force, CY. Okay, so now I want to talk about this internal force. Okay, this is a bit messy. Let me go back. Okay, talking about this internal force, so we need to use this positive sign. So this will be the positive sign. Okay, and this positive shear, and then this positive axial. Okay, so if you look at this, it is like a smiling face, the positive moment, just to keep you, maybe you can remember well. Okay, so when your beam is bent like this, okay, so you are positive. So your moment is acting in such a way. Okay, so let's put this arrow, okay, this arrow, this arrow, this arrow in our cut section as the internal force. Okay, so when we come to here, okay, so let me draw a cut section here. If you want to draw a positive sign, the shear must be at this right, okay, it must be going down, and then this must be upward. Okay, this is the shear. This is the positive sign. We always draw at the positive sign, so that when we solve for the equilibrium equations, when we get the negative, we directly know that this shear is in negative. Okay, so let's have a look back on this. If you can see that, this is if you cut a section at left, so this is going up. Can you see that? Okay, this is at this side. Okay, this is how you see. Okay, when you cut it here. Okay, so when you cut it here, this moment is clockwise. Okay, so this is going up. Okay, this is also going up. So if you can see that the moment is always acting up. Okay, but if you want to remember from this one, you depends on where is the cut section side. Okay, either you want to cut it and then to look at this right section, so this will be counterclockwise. Okay, So now we want to put in the axial. Axial force will be always going out, just like thrust as well. Okay, going out from the joint. Okay, so this is the equilibrium at this particular joint. Okay, then we put it back here. So if you can see, the shear is going down when you cut the right section, okay, right side. Okay, and the moment is always going up. Okay, going up in such a way, either counter clockwise or clockwise. Okay, so make sure this you have applied the this positive sign. But why there is no axial force here? Anyone? Class?
Because the external load is perpendicular.
Yes, because there is no horizontal forces in this case. Even though we have AX eventually will become zero because this P kilonewton is straight. Okay, unless this P kilonewton is diagonal. Okay, therefore there will be a horizontal system in this case, and there will be axial force. But in the correct way, you shall also have an axial force. But now, it can be taken out because they know that this is equal to zero. Okay, and their intention now to solve the shear and the bending moment. Okay, good try, huh? Okay, this is the procedure for analysis. You can have a look, okay? But the main concept is on the cut section, okay? We cut the section, we put on this equilibrium free body diagram of a section, and then we solve by the equations of equilibrium. It is quite similar, okay, to the thrust analysis. Only right now we are deal with bending moment, okay? Okay, there are more reading slides that you can go through later. Okay. Okay, this is a guideline, okay, to draw a bending moment diagram and shear force diagram. We will go back to these slides later. Okay, this slide as well. Okay, we will go back to these slides. Okay, let's start with these examples. Okay, so now we want to determine internal shear and internal moment, meaning that the shear force and bending moment at point C and at point D. What is the difference at point C and point D? Actually, it is at the same point. Okay, just they enlarge this size to just to tell you that C is after this 5 kilonewton and this D is before the 5 kilonewton. Okay, then what is the difference? So what you need to do is you need to cut section, this beam section. This is a cantilever beam. Okay, if you idealize this, it is actually a fixed end here, and this your beam, and with 1 kilonewton apart, they are 1, 2, 3, 4, 5. Okay, 5 of this 5 kilonewton, and then there is 130 kilonewton meter. Okay, so this is how you idealize it. So now the question asks you to determine the shear force and bending moment before and after this 5 kilonewton. Therefore, you need to cut a section after and before. Okay, you are going to solve this beam twice. Okay, one is cut section CC and the other one is cut section DD. Okay, first of all, we need to know how to cut a section. Okay, now you have decided on where to cut a section. The next is which section you want to analyze. Okay, may I see my next slides? Okay, so maybe I will draw it here. Okay, let's see. Okay, now we have idealized just now. Okay, if and with all the lots. Okay, now we want to cut the, let's say, CC. Okay, so meaning that when if this is CC, when you have decided, you need to check whether you want to analyze this section 1 or AC, section AC, or section CB. Okay, this is C is here. Okay, so if you want to consider the section AC for your analysis, this will be your free body diagram. So you will have A and C here. It should not be C, it is somewhere X. Okay, but if you already know exactly at C, so you want to determine at C, not at X, so it will be at C. C means you have 2 meters. So now you have to draw all the forces, okay, in this section AC. So you have AY, you have AX, and you have MA. So this is all assumed direction. Okay, but at C, you are going to put in a positive sign. Okay, so where it should be going down, positive, and going upward, moving counterclockwise. Okay, as the positive sign. Okay, when you cut at this right side. Okay, and then you need to put in all these forces. Okay, this is after 5 kilonewton. Okay, or okay, you choose section C. This is section AC. You choose section CB to analyze. Okay, then this will be C here. Okay, C, and then this is B. You need to put in all the forces, okay, within this. So you have 1 meter, 1 meter, 1 meter. Okay, so you have this 5 kilonewton, 5 kilonewton, 5 kilonewton, and then the 30 kilonewton meter. Okay, so here at this cut section, you need to be able to draw a positive sign of the shear. So it will be going upward and also clockwise bending moment. Okay, so this will be always drawn in this if you are considering a left section. Okay, so now you have these two sections, free body diagram. These two, so but you have this is I have to show you how to draw. Okay, if you consider the right side and if you consider the left side. Okay, so if you are more familiar on that, okay, by observation you need to directly choose the most maybe convenience, easier section for you to solve. Okay, if you can see that if in AC you need to solve for all the A support reaction first before you solve your V and moment. But in this case, in section CB, you can directly solve for your shear and bending moment. Okay, that is why in this case, they choose section CB, okay, to analyze, okay, the system instead of AC. Okay, if you can see that. So this is the free body of CB. Okay, you have choose one of the section to analyze, to solve for all these internal forces. Okay, so I will start with solving these forces. If you can double check your positive sign of the shear, moment, direction. Okay, all the forces are here. Okay, then you can start. You can use summation Fx, Fy, Mc. Okay, but in the beam, if there is no horizontal force, normally we will use Fy and also summation moment. Okay, if you look at this summation Fy equal to 0, you need to gather all the positive, all the vertical forces. So there will be Vc. Okay, following these assumptions here. Okay, going up is positive. So the rest of 5 kilonewton is actually going downward. Therefore, it's -5, -5. Then you solve for VC equal to 15 kilonewton. So the next is you use the summation moment, okay, to solve for MC here. Okay, so if you look at summation moment and at C equal to 0, meaning that this VC and NC will be eliminated in this equation. Okay, you don't need to care about this. Okay, the next will give you a moment will be from this 5 kilonewton. Okay, this 5 multiply the distance 1. And then the other 5 kilonewton, further 5 kilonewton multiply the distance to C is 2 meter. And then the next 5 kilonewton to distance C is 3 meter. Okay, therefore you have 5 times 1, 5 times 2, 5 times 3. And then you have the last one is the moment, 30 kilonewton meter. So once this is already in moment, you no need to multiply with the distance because it is already in the unit of kilonewton meter. So now you have to put in the 30. Okay, now double check on the sign. Okay, so this the first 5 kilonewton is acting to C in this direction, clockwise. Similarly to this, the second 5 kilonewton and the third 5 kilonewton and also 30. So all of them are clockwise. Okay, but this assumption here, it put a counterclockwise as positive. So, but it will be up to you, this assumption, if you want to put a clockwise as positive. Okay, this one. Okay, so as long as this can follow the right assumptions. Okay, but now since it is counterclockwise is positive, so this clockwise will be negative, 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 correct? And then this MC also clockwise. So all of these moments are in negative. Then you can solve for your MC. MC is negative 60 kilonewton meter. Okay, any question, class? Am I too fast?
No.
Okay, it is quite, maybe I will ask one or two to confirm. Listen to me well. Okay, where is my student, my class? Okay. Ezatu, Husna? Hi. Husna, are you here with us? How about Nur Shafika?
Yeah.
Yes. Do you understand what have my class? Yes, it's quite slow. So if you have any question, please stop me. So right now I will continue on the next slide. Okay, now I want to solve for internal forces at D. Okay, what I need to do is just to cut a section. Yeah, before this 5 kilonewton. So then you need to draw the free body diagram of the section. Okay, similarly, we were taught that analyzing this section would be more easier because you no need to determine all the AX, AY, and the support reaction at A. Okay, so if you want to choose these sections, so again, maybe a bit slow in this first example. Okay, so now you are going to draw this free body diagram for this section. Okay, now this is supposedly DB. Okay, this is before the 5 kilonewton. Therefore, the 5 kilonewton must be drawn here. Okay, so similarly, we put in all the forces. And put in all the geometry. And lastly, put in our internal forces. Okay, may I know the shear force? The positive sign is which direction for shear force? For this, yes, Thank you.
Upward.
Yes,
Upward.
and how about the moment?
Clockwise.
Thank you very much. Okay, so this is how you draw these internal forces, and also actually you have a exert force coming from out from the joint. Okay, now you can solve this. Okay, so as I'm not going to go very detailed right now, so still using the summation Fy, okay, and still using the summation moment. Okay, now they choose D equal to 0. Okay, so once you solve for this VD and MD, okay, we can actually prove something here. Okay, even though C and D is actually at the same point, actually the C and D is at the same point here. Okay, but they are looking one before 5 kilonewton and one is after the 5 kilonewton. Okay, then what, if you can see the result here, VC after the 5 kilonewton is 15 kilonewton, and VC before the 5 kilonewton is 20 kilonewton. They are varies in terms of shear of how much? Of 5 kilonewton, because of this existence of these loads. Okay, but the moment, okay, at D or at C is negative 60, and at D is the same. Okay, they don't have any effect due to this 5 kilonewton, unless at this particular position is not 5 kilonewton, but in term of moment, 5 kilonewton moment. Okay, so at least from this exercise, we can prove on something. There is some changes in the shear, okay, even though they're actually at the same place. All right, I would like to
Madam.
yes,
So is it okay if VC have two different value? So the answer is two different value.
yes, correct. The answer is two different value. So when you draw the shear force diagram later, at that particular point, you are going to have two values.
Okay, thank you, madam.
So next, I would like to show on this triangular loading. Okay, so let's try to draw this shear and bending moment diagram. Okay, so there are several ways to draw this diagram. We can use the equation, the shear and bending moment equations. Okay, derive this equation, and then we put in the values that of interest in that particular equation. Then we can get the shear force and bending moment, okay, at that point of interest. Okay, and the other method is quite popular also is the area method. Okay, so we will go have a look on these two methods. Okay, but I will focus on the derivation of this, establish the shear and bending moment equation. Okay. So now, if you look at this problem, let's say A and B, okay, so there is loading 20 kilonewton per meter, increasing from A to B, or sometimes we said that this is a triangular loadings. Okay, but these loading are in a line. I mean, if you can see that they are proportionate, okay, directly increase. This is gradually increase, but they comes from one slope. Okay, therefore you only will have one equations, okay, along this A to B. Okay, you no need to cut each of these one section, and so on, because this is these equations, this loading can come with one equation, because this is in specific slope only, unless you have something like this. You have two different slope. For example, this is 10 kilonewton per meter, and this is another one is, sorry, this is 50 kilonewton per meter. Okay, so even though this is already trapezoidal, but I would like to show you is this one and this one is different slope. Therefore, you cannot use the same equations for this these sections. Okay, you need to cut it. Okay, now let us try on this, solving this simply supported beam. Okay, so here these slides we will see on how to determine the support reaction. Again, we use the support, we use the equilibrium equation. Okay, so in this case there is no horizontal force. I start with summation Fx equal to 0, Ax is equal to 0. Okay, so because there is no other horizontal force except this Ax. Okay, so and then you can take a summation moment. Okay, it choose A equal to 0 because you want to eliminate most of this A. Okay, Ax and Ay unknown forces, but Ax you already know. So you can start summation MB equal to 0. Also, yeah, no problem. Okay, so let's see. Okay, now you have this loading By and also 20 kilonewton per meter to be considered. So when you have this some sort like distributed loading, okay, you need to determine the resultants of this loading. Okay, so if it is UDL, okay, rectangular loading, okay, so the you are to get this resultants, you are talking about this area of the rectangular. Okay, similarly for triangular loading. Okay, if you want to take this resultants, it will be talking about the area of this triangular. Okay, so let's have a look the area. The area will be, I cannot write, half time the height time the base. So this is the base, this is the height. Okay, then this you get the resultant forces here. Okay, so this one, if you have a rectangular, then you need to know the height and you need to know the length. So let's say the height is, normally we put a W, so it will be WL. Okay, so now we go back to this triangular loading. Once we know the resultants, we need to take moment, right? So we need to know that this resultant is acting on which, where is the location acting, okay, within this 9 meter. Okay, it will be act on the centroid of this area. Okay, so it will be always close to the highest value. Okay, so with 1/3. Okay, distance. Okay, and the other distance will be 2/3. So now, how about the rectangular? It will be, where is the centroid? It will be half. Okay, so we go back to this triangle. We want to take summation moment at A equal to 0. Therefore, we will have to determine the distance from the resultant, okay, to the A. So this will be the distance that will be used. Okay, so you'll be half. This is the resultant. Half 29 that we already found here, right? And then this will be the distance. Okay, 2/3 of the length. The length is 9 meter. Okay, then the next will be the By. The distance to A will be the 9 meter. Okay, then you check on this the direction of the moment. Okay, By is acting, okay, counterclockwise, and this triangular loads is acting clockwise. Okay, so you can solve the By right now. Okay, so now for this rectangular, I would like to to also explain on this rectangular how to take a moment if you want to take it let's say at A. Okay, so moment A here will be actually equal to, okay, the resultant forces WL and multiply the distance to A will be L over 2. Okay, so of course this is in negative lah, because when you want to use the summation moment later, you can try. Okay, it will be in the negative form. So it will be WL squared over 2. Okay, this is for the case of rectangular. Okay, let's come back to this example. So now we already solved for BY. Okay, we can use the summation FY equal to 0 to solve for AY. Okay, we know that AY plus BY is equal to this triangular loading. Okay, the triangular loading will be the resultants here. Okay, so you can solve for AY or your support reaction right now. Okay, now I will show you on how to establish the equation at section. Okay, so there is no much different. I think the most challenging one is to draw the free body diagram correctly. Okay, so let's see. Okay, so now as we know that along this 9 meter, there will be only one equation. Therefore, we are going to establish the shear force and bending moment equation cut only at one section. So any section at this 9 meter would do. So we are going to cut it here. Okay, so you can either choose section 1 to analyze or section 2 to analyze. Okay, in this case, okay, we are using this section 1 to analyze. Therefore, all the section 2, so you just not free body diagram. Okay, but here, this height, when we cut here, okay, at let's say at point O or X, okay, point X, we don't know what is this value. Okay, it will be in terms of X. Okay, when we cut at X, this height, we do not know the value. We know that at 9 meter, it is 20 kilonewton meter. But at this X, what is the height of this loading? So we need to determine that loading, this amount first. Sorry, this one. So we are going to use the proportionate method or ratio method. Okay, so it will be in such. Okay, so we have two information here. If this is 9 meter, we know that this is 20 kilonewton per meter. Okay, but if this is X, here, let's say X, we do not know how much is this one. Let's say W. Okay, we do not know the height of this. Okay, so you can use this method. 9 is 20. Okay, so X would be okay, so or this is what I always use to get the proportionate or ratio problem solved. So if you have this first relations, okay, this is 9 meter is the length. Okay, the height is 20 meter. So now I have another length is X, and then my height for the X will be this value 20 divided by 9 and multiply with this X. So this will be the value, okay, for the height of this loading, 20 X over 9. Okay, any questions? Anyone do not understand what I'm doing right now?
I'm not understand.
Huh? You don't understand? Can I? Okay, very good. Okay, at least I have a feedback. Okay, now I discard everything first, huh? To make it clear. Okay, so now I want to cut a section and draw a free body diagram of my this section. Okay, so I know that along this 9 meter, I have only one loading, which is increasing. Okay, so I know that I only need to cut one section. So I will cut a section here. Okay, so then I need to draw the free body diagram, either my part, my right part. I have decided I just want to analyze for my section 1, okay, which is the left part. Okay, therefore this will not be included in my free body diagram because I just want to analyze my left part. Okay, so also section 1. Okay, but now the problem comes. We know that at 9 meter, the loading is 20 kilonewton per meter. But when I cut a section here at somewhere at X, we do not know the value yet. Okay, we don't know what is the height of this load, right? So now I need to determine, okay, based on the ratio, what is the height? Sorry, I want to draw this question mark. Okay, what is the loading of at this one so that I can draw my free body diagram correctly? It is not 20 kilonewton per meter. So we can use your triangle to represent our problem. Okay, so at for 9 meter length, we know that the height of this load is 20 kilonewton per meter. But when it is X, now when this is X, height, length here, I do not know what is the value of this W. Okay, so I can form one ratio problem here. So I put this value appropriately. With this is the length, and this is the height. So length here I have 9 meter. And the height for 9 meter is 20 kilonewton per meter. Okay, and my unknown length here is X. Okay, and my height should be W. Okay, so to get this W, I can use this method, okay, by ratio, which is always divide and multiply. So 20 divided by 9 multiply X. Okay, you have solved your answer, your question. So means that this height will be 20 over 9x here. Okay, this is, of course, this is one of the methods. You might have other methods that is more suitable. Okay, class, can I proceed?
Yes.
Okay, what I want to show just now is just to get the loading, this one. Okay, because this is no more at the X distance of X, it is no more 20 kilonewton per meter. It will be in terms of X. Okay, yeah? So now once we have this, can I discuss this? Okay, so while we have this, we need to draw all the informations from this cut section. Okay, we need to include the AY. Okay, what else? This loading we already put it in. Okay, it should be in this way. So this is 20 over X, 20X over 9. And then we need to draw these internal forces. It should be in positive sign. So going down is shear force positive, and counterclockwise is positive moment. Okay, that's all. This is your free body diagram. Okay, so this is the resultants. This is not, this will be later. Okay, this will be explained later. Okay, so next we want to solve and establish equation. Okay, we will take summation Vy equal to 0. Okay, so remember now this is X. Okay, so and then we start to put this triangular loading into the reaction. How to get this reaction? We use this area. We determine the area of this triangular load. So it will be half the height and the length. Okay, so this will be your resultant forces. And where it acts, it will act 1/3 to the highest loads. Okay, x over 3. Okay, but now we just want to get the summation Fy equal to 0. Okay, so we will talk about the 30 kilonewton. Then we'll talk about the reaction. The resultant force is going down. So it will be, this is the resultant force. And can you help me on this? It will be, can you take this out? Okay, so this is not done yet. We have included 30, we have included the resultant, and another one is the V. V is minus V. You should put it here. Then equal to 0. Okay, then you can solve V. Can you check whether this is correct? Let me check also. Okay. Yes. Okay. So can you erase this in my notes? Okay, that is not supposed to be like this. When you have a summation Fy equal to 0, there will be 30 kilonewton. Okay, in this free body diagram, we have 30 kilonewton. We have the resultant forces done, and this is negative, correct? And then we have a V going down, minus V. Okay, minus V, then equal to 0. Then we can solve this equation and put this V at the left, then equal to the rest to the right. So this will be your equation for shear force. Okay, so please help me to put it Vx here. Okay, so when you have a Vx equations done, you can determine your shear force at along your x until 9 meter. So for example, if I want to know x equal to 0, what is my shear? So you just substitute the x into this equation. So for example, my shear at 0, it will be 30 kilonewton. When I put the x into this equation. When x equal to 9 meter, okay, then just put this 9 into this equation. Okay, is negative 60. Am I right? Can you check for me? Sorry, it's not meter. Okay, do you understand what I'm trying to do right now? I'm establishing the equation for shear force. Class?
Yes, madam.
Okay, huh?
Okay.
Okay, so now I want to establish the equation for bending moment. Okay, so I want to discuss this first. Have you taken anything, the notes? Because I'm going to erase this now. Okay, let me erase this. Okay, now we go back to this free body diagram, and I want to determine my bending moment equation. Okay, so the bending moment equations here will be taking m counterclockwise. Mx equal to 0. So it should be x. Okay, so now let's try. Okay, we want to take this moment here, x, okay, is 0. So we have 30 kilonewton and the distance is x. What is this question about? This is just to draw a bending moment. All right. So I suppose in this question they solve the I mean a particular point, the moment at x equal to 5.2, but I don't intend to solve for at the particular point. I want to get the bending moment equation. Okay, can you help me? This one will remain as x. Okay, because we want to get the equation. It will be in terms of x. So first of all, the moment will be 30 times x, negative. Okay, because this one, they put in the positive sign. Okay, so next will be the resultant force. Resultant will be half 20. Can you put this one as x? Okay, so you will need to put these resultants here. Okay, this is the resultant as well. Okay, this is all the resultants are here. Okay, next we multiply this resultant with the distance to the x is x divided by 3. X over 3. Okay, so it will be acting counterclockwise. Therefore, it is positive here. And then the last one will be this moment in the system. Okay, there will be also counterclockwise. Okay, also positive here. And then plus mx equal to 0. So now you need to remain the mx at the left and the remaining go to the right. So can you form an equation for me here? Now in your notes. So this will be negative 30x. This will be plus Can you check whether I'm done? I'm doing it correctly. My calculator.
Yes, madam, yes.
Okay, thank you. So now we can put in, if we want to find the value of this moment when x. Okay, now I'm using this equation. Okay, to determine if I want to know the moment when x equal to 0. Okay, what is my moment? Okay, it will be 0, right? When x equal to 9, okay.
0.
Yes, 0. So this is a very true. If you are familiar with simply supported beam, okay, there will be a 0 moment, okay, at the pin and also the roller, okay. So once you,
Yes.
of course, you want to determine the maximum, right? Okay, so we will have a look on my next slide. Okay, so make sure you tidy up these slides. Okay, rewrite probably better. Okay, on how to get this shear equation and also bending moment equation. Okay, So that you
Madam,
can do, yes,
okay. For shouldn't be the 30x is positive?
30x.
Yeah, negative 30x should be positive, I think.
Because our earlier assumption here, okay, this maybe is quite confusing. Our earlier assumption here is counterclockwise positive.
I mean for the final equation of mx.
Oh, okay, wait now. Yes, thank you very much. This is positive and this is negative. Okay?
Okay, madam.
Now okay?
Yes, thank you, madam.
Yeah,
Okay,
thank
okay.
you very much. Yes. When we go, we put this to the right, it should be turning to positive. Yeah, correct? Yes. Thank you. Okay. So next, we will see on this draw the this shear force diagram and bending moment diagram. Okay. So there are two methods here, but actually, area method is very popular method. But when it deal with this area with this with the curve, you might be prepared with some of these equation where you have this power of equation, power 2 or power cube 3. Okay, so you might have a challenging one, okay, for area method. Okay, but now I will show you on this using the equation. Okay, just now we have determined okay, sorry, I have erased just now. If not mistaken, when x is equal to 0, the v just now is 30. And when x is equal to 9, the v is negative 60, is it? Yes. So now once you have obtained all these interest, value of shear and value of bending moment at the point of interest, okay, then you can plot it in your shear force and bending moment diagram. Okay, so for example here, you plot it, you know that this is positive 30 at 0, okay, and this is negative 60, okay, at 9 meter. So this you can get the shear force diagram, the 2 point. But now it's the matter of what is the shape of your shear force diagram. Okay, so the next will be the bending moment. Okay, we have determined that this is x is equal to 0, m is 0, and m at 9 also 0. So we can plot it here. We know that both of this moment is acting 0. Okay, but this is not sufficient. Okay, we know that when shear force is from the positive shear to negative shear, okay, they will be passed through this axis, okay, where you have a zero shear force somewhere that we do not know, and we need to solve it. Okay, so how to solve this? We need to get back to the shear force equation. Okay, so when we get back to this shear force equation, okay, we know that the maximum moment will happen at where the shear is equal to 0. So now we already have this shear force equations solved here. We just put it a statement that v is equal to 0. Then this v equations is equal to 0. Then you can solve the x value here due to v equal to 0. Okay. Again, just to repeat a quick one. Now we want to determine the maximum moments. Okay. And we know that the maximum moment will happen when this v is equal to 0. Okay. So, but we do not know what is this value of x. and we need to go back to our shear force equation. Okay, this shear force equations is already established earlier, which is this one. Then we need to put it equal to 0 because we want to determine when V equal to 0, what is the value of X. Okay, so from here, you solve the X is equal to 5.2 meter. Okay, so meaning that 30 going to the, and then you solve for this equation. Okay, so once you get the 5.2 is 0, so you can know that the moment will occur at the 5.2 as well. So what you need to do, you need to put in this X equal to 5.2 meter to your moment equation now. Okay, so another one is when X equal to 5.2, what is your moment at 5.2? Okay, putting into this moment equation, then you can find that this is 104. Okay, please try later. And you can't know that this is in this shear force and bending moment diagram. Okay, this you draw a positive at the top. Okay, shear force as well. You draw a positive at the top. So once you get the positive 104, so you plot it here. Then you need to guess. Okay, what is the shape? Okay, so for guessing the or predict, or when you come more familiar, okay, you will know how this shape form. Okay, but for the guideline, please have a look on this. Okay, so I will maybe spend another 2 minutes on this. Okay, so if you look at this few very popular cases. Okay, so these are the shear forces. Okay, shear force diagram, and these are the bending moment diagram. Okay, so if you see that this cantilever beam, why we say this is cantilever is because there is one end with free end. There is no support at this end, but at the other end it must be fixed. Okay, if it is pinned, this is unstable structure. Okay, so if you look through the span, there is no other forces except of this P kilonewton or Newton. Okay, so therefore this at this end you will have summation Fy. When you solve it, you will have P as well. Okay, to counterback this P, and to counterback this moment, you will have PL. P multiply the length L, you get the PL. It should be opposite way of your applied loading, so that this will achieve the equilibrium. Okay, now we will draw the shear force diagram. Okay, so this will be the straight line. Okay, because there is no other forces. Okay, along this length. Okay, so the shear will be at the straight line. Okay, so when the shear is at the straight line, this moment will have a straight line, but at this increasing or decreasing slopes. Okay, depending on your shear value. Okay, but right now we have a PL. This PL is negative sign. So therefore, in this direction, this is negative sign. If you still remember our cut sections just now. So now we have a negative PL. Okay, so we have at the other end, it will be moment equal to 0. So when you are drawing this bending moment, you need to draw when the shear force is a straight line. Okay, so this moment you need to draw a straight line as well. Okay, when the slope is 0, okay, if you can see that these slopes, we have a increasing or decreasing, but we still draw a straight line. Okay, so for come to this this case where you don't have the second case here I am with, so we don't have any loading on top of our length, only moment. So in this case we don't have any horizontal or vertical reaction, only moment. Okay, when acting in this direction, okay, clockwise here, we have a positive value for moment. But here we don't have any shear. So this one, we don't have any shear. And if we don't have any shear, then we have a flat. Okay, this is flat moment. Okay, flat. We don't have any increasing line or decreasing line, only flat. Okay, so this moment will be just like your shear just now. Okay, because only have moment. Okay, third case. Okay, so if we have this increasing, not increasing, distributed loading, okay, UDL. Okay, so we can determine our reaction, okay, which will be WL. Okay, the resultant of this rectangular will be WL. Okay, and this length, I mean distance to the supports will be L over 2. Okay, once you get this support reaction, you can plot the shear WL here, and you need to minus, okay, minus this W naught, okay, because this is your starting point of the shear. When there is a downward forces along the L, it will be minusing, okay, the shear until the end of this length. Okay, if you can see that if you are dealing with this UDL, the shear force is within this slope, with this straight line, but sloping. Okay, when you have a sloping shear, you are going to have a curve moment. Okay, with a curve here. Okay, similarly for this one, if you have a curve at the shear force, you also have a curve in the higher power. Okay, for your moment. Okay, so now in our case just now, we are having this one. Okay, where we have a curve. So for the moment later, we are also having the curve. Okay, but which direction? Either this direction, okay, or this direction, okay, or this direction. Okay, this is going up. Okay, this is going down. Okay, so let's have a look back to our example just now. Okay, so now if you look at this, this is in the curve like this. So this is due to your loading. When your shear is in this way, okay, so this is due to this loading. Okay, because this loading is increasing from 0 to increase to 20. When this load is increasing, meaning that the slope increase. So if you draw this one, if you can see that this is gradual slope. This is higher slope, steeper. Here, if you can see that. So you have to plan in such. Why? Is because your loading is increased. Okay, but if your loading is decreased in this way, okay, if your loading is decreased in such a way, okay, you need to plan such that this your shear force will be in such. Okay, the curve will be in such, okay, where you have a steep first and you have a gradual here. Okay, so this is some curve that you need to play around. Okay, if you are not familiar with these curves, okay, what I would advise you is to plot, okay, a few more. Okay, what is the x at 1 meter and 2 meter and 3 meter, then to plot few of these points so that you can visualize how the bending moments being drawn. Okay, so similarly to this one, okay, so if it is positive shear, we are talking increase, going up, okay, going up manner, okay, this is going up manner, okay, but either this direction or this direction also going up, right? I mean this type of curve 1 or curve 2 also going up, but right now this shear is decreasing. Decreasing means that when you are going up, you shall achieve a gradual slope. Okay, from steep to gradual slope. Therefore, you choose number 1 for your curve here, this part. Okay, so I think you can explore further with the exercise I given to you. Okay, later. Okay, so this is the area method. Okay, area method, maybe this is a bit tricky. Okay, more challenges. Okay, you can have a look, and I can share you later the video that related to this using area method. Okay, so I don't think I can go to this example 3 with you today. Can we take a 5-minute break, and then I share with you another example. Okay, so
Okay.
yeah, besides I want to go to UFuture and have a look on our attendance. Okay, so we have Abdullah Amin. Are you with us right now?
Yes.
Okay, can you go and take your attendance in UFuture?
Okay, madam.
Okay, 1B clear. Okay, 5A clear. Okay, 5, yeah, clear. So only Amin, Amin, please help me to take your attendance. And then I actually go through the I discussed yesterday and have a look on any post from your group. Okay, do you have any problem in this I discussed problem tutorial?
No.
No, so any others? We have actually 40 students in this class. It's quite a big class. Do we have all here? We have 2 not in this room. Maybe they have a problem. Okay, can have a look later who is not here. Okay. Okay, give me rest for another 3 minutes. Okay, we will start with one examples where you need to write out. Okay, we will go through together. Okay, on that particular example. I've also created the week 2 I discuss. Okay, so quickly done your week 1 exercises, I found there are 5 posts: Dayang, Eliani, Aina, Elvira, Faris. They are very familiar faces. Huh? Okay, so how about the rest? Okay, let me see. 1B. Oh, 1B, we have 1 post, Nurul Nabila. How about the rest? Okay, we have 5A. We have 14 students, but I haven't received any reply from you. Okay, and then 5B. Same to 5B. Okay, so if you have any problem, always give feedback to me. Okay, I'll try to guide you through, and then try to have connected to your friends, and you can still do a group discussion. Okay, for these particular exercises. Okay, yeah. So give me. Okay, class, I would like to start with one example here. Can you do together with me?
Yes, yes.
Okay, yeah. So
Okay, madam.
please, can you see my slide right now?
No.
No, okay, sorry. I show
No.
you. Okay, wait now. Where am I now? Can you see example?
Yeah.
Okay, so we are going to do this example. Okay, please take down this problem. Then we will start with solving the support reaction. Okay, I give you a minute. Okay, we will start now by solving this support reaction. Okay, now I have only pin at B. So I have BY here and I have CY here. Okay, so I will take this summation moment. Okay. Summation moment C equal to 0. Okay, and I have put this clockwise as positive in my assumption. So now I want to determine my support reaction. Okay, so I will have loading like 25 kilonewton meter, 75 and 120 kilonewton per meter, BY and CY. Oops, not CY. CY will be eliminated in this case. Okay, so can we start with 25? Is it positive or negative? We will start with this 25. 25 is, yeah, thank you. 25 is negative. Okay, then 75 is negative or positive in this case? We take a
Negative.
summation. Yeah, it is also acting on this counterclockwise. Okay, the force is 75 and the distance will be 2 meters. Okay, and then how about BY? Positive or negative in this case?
Positive.
Okay, positive BY. And the distance to C, the distance BY to C is 1 meter. So I will not write anything about 1, so I will put BY. Okay, the next will be 120. Okay, the resultant force of this 120 kilonewton per meter is acting at the center here. Okay, so the resultant is the area of the rectangular, which is 120 multiplied 1. Okay, also 120. So now it is also negative 120. Okay, time 1. Okay, you might skip that and time half of it. Okay, which is the distance. Okay, to C. Okay, then equal to 0. So can you solve BY for me right now?
235.
Thank you, 235 kilonewton. So now I'm going to proceed to find the CY using summation Fy equal to 0. Okay, so now we have 75. Now I want to change color. Okay, change to green. Okay, so I have 75. I have BY, I have CY, and I have this 120. Okay, so let's put it into this equation. Okay, going up is positive, so therefore 75 is minus. Okay, BY is positive. Okay, CY is positive, and 120 is negative. Okay, so therefore I put in this equation, and also I can substitute this 235 into my equation. Okay, therefore, can you help me? What is the value of CY?
Negative 40.
Okay, is that true?
Yes, yes.
madam.
CY is negative 40. Okay, thank you. So now the CY is actually going down. So be careful. It's not upward, it is downward. Okay, now once you get this support reaction, we want to determine the equation along this beam. So how many cut section I shall have in this case?
Three.
Where? From where to where?
From C to B before B. Wait.
A
Two.
and before B.
Okay, yeah. I try to understand why you say this answer 3. It's because you want to cut a section before this 120 resultant force and after, is it?
Yes.
Yeah, you
Yes.
should not do that because in the real case, it is not 100. It is not 100 kilonewton. It is 120 kilonewton per meter. Okay, we put it in the resultant force is to make us easy to get this bending moment. Okay, so I will, in this case, I will take this out so that you won't confuse this. Okay, so now we will have only two cut section. Okay, because this 120 kilonewton per meter is in terms of one equations only. Okay. So now let me put in this Cy. Cy is 40 kilonewton, but going down. Okay. This is going up. Okay. So now I would like to, can I erase this directly? Okay. So now I would like to draw cut a section. I will cut two sections in this case. Okay. First of all is this one. Okay. Let's say this cut section. 1, let's say. Okay, so now I will consider either my left side to analyze or my right side to analyze. Okay, so which one you prefer? Left side or right side?
Left side.
Left side.
Left.
Yeah, because it is more simple. Okay, for me, maybe for you too. So now if I consider this left side, the rest of the remaining here I will not consider, only this. I will consider only this part. Okay, so I will draw my free body diagram right now. First of all, I need to name it. Okay, so I will name my section is X1. My cut section 1 is from 0 to 1 meter because I'm cutting A to B. After the B, the equation will change. The shear force and bending moment equation will change because there is some changes in terms of loads. Okay, so that we'll do it later. Okay, now this is our naming of the section. Section X1 from 0 to 1 meter. Okay, now I draw my free body diagram. So this is my free body diagram where I need to put in all my loading. 75 kilonewton, 25 kilonewton meter, and also the cut section here at X1, the distance. Okay, but the X1 will be varies from where? From 0 until 1 meter. Okay, it will be. Okay, so this is our equation. Then we need to draw the internal forces in the positive sign. Okay, so the shear force is downward and this is counterclockwise moment at X1. Okay, so then we can start with this summation, taking summation, moment. Maybe I'll put it here. Summation moment X1 at X equal to 0. Okay, so let's start summation M X equal to 0. So we will have to take into consideration the 75 kilonewton and also the 25 kilonewton meter. Okay, so the 25 kilonewton meter, there will be negative 25 because it is counterclockwise. and also the 75 will be also counterclockwise. And the distance to x1 is x1. Okay, we are talking about this O. Maybe you want to put it x here, or maybe O. Okay, so let's say we are putting this O. Okay, so and then another moment, okay, that involved in this free body diagram is this mx1. Okay, so you need to put it mx1, also negative because of the direction. Okay, 0. So now your mx1, you can get the equations, okay, which is negative 25 minus 75x. Okay, so later you can put in a statement when x equal to 0, what is your mx1? When x equal to 1 meter, what is your mx1? Okay, you can get it the value. Okay, I will give you the answer later on this. So next, I will move to the shear force equation. It will be using, we will use the summation Fy equal to 0, and my assumption is upward. Okay, now in this case, I have 75, which is going down, and I have also Vx, also negative going down, so equal to 0. So you can get your shear force equation, okay, which is negative 75. Okay, so if x equal to 0, x equal to 1, both of it will give you Vx equal to negative 75. Are you okay, class?
Yes.
Yes.
Okay, so can you get this? When x equal to 0, what is your mx1?
Negative 25.
Okay, when x equal to 1?
Negative
Negative
100.
Negative
100.
100.
Okay, so if you want a more proper, you put in the units. Okay.
20.
So this is how you do your, your equations for the bending moment and shear force, and also you get the value lah at the point of interest. Okay. Can we go on to another section? Okay, to finish it. You have class later?
Yes. Yes.
You also have class later. So maybe a very quick one. And shear force diagram and bending moment diagram, maybe you need to continue by yourself. Okay, maybe I will just to make sure this is done completely. Okay, so now I want to cut a section, okay, at here. Okay, so now this will be okay. This will be 2, 2. Okay, so if I still continue with finding my considering my section, the left part, it will be draw something like this. It will continue with 75, 25 kilonewton meter, so 1 meter A, and this B is 235, and this is UDL of 120 kilonewton per meter. And you have a cut section, and then you have this shear force, and then you have a bending moment here. Okay, but now the x2, the naming of this section will be x2. x2 is from where to where? You can start your x2 from here, there is no problem. You can start your x2 from here, there is no problem. Okay, so now in this case, I would like to show you when your x2 is start from here. So this means that you are from 0, is from 0 to 1 meter only. Because you are talking about this section BC. Now you are looking at section BC, cut section for member BC. Okay, so now we can continue with taking a moment, summation moment equal to 0. Do I miss out anything? Let me see. 75, 25, okay, 235, okay, Vx and x, correct? So this is number 2, right? Okay, so now to get this moment equation, I will need to copy actually your previous moment equation. Okay, negative 25, negative 75, x1, okay, and negative mx2. Okay, so actually I can recopy everything from my previous calculation. Negative 25, negative 75. Oh, but now it's not x. The distance is to the cut section will be 1 meter plus x2. So it will be 1 plus x2. Okay, then we continue with the plus 235, and the distance is x2. And then we have this 100 kilonewton per meter, which the resultance, okay, is 120 x2. And the distance here is x2 divided by 2. Okay, so it will be also negative 120 x2 is the loading, and the distance is x2 divided by 2. So this is your moment equation. Oops, missing another one is the mx2, which is also negative. So now please help me to find what is the mx2 later, okay, to form this equation. Okay, I will continue with summation fy equal to 0. Okay, so now I have 75 with me. I have 225, and I have 120 x2, which is downward. And then I have minus vx2 equal to 0. So now you can form your vx2 equation, okay, by rearranging these elements. Okay, let me check whether I have missed out anything. Yes, okay. Okay. So, okay, class, sorry for taking another 5 minutes from you. Okay, so now I have shown you on how to write an equation, okay, and then how to decide on the way to cut a section. Okay, so any question from you? If not, I will see you next class.
No.
No question, madam.
Okay, so I will need to stop the recording. Okay, for those who have an internet problem, you can get this video later lah. Okay, so but this is quite a bit lengthy, yeah. Okay, but I hope you get the idea of today's class. Okay, so for the tutorial in iDiscuss, please complete the first week tutorial, because every week I'm going to give you exercises, okay, so that you won't be left out. Okay, so I see you again next class. Thank you for coming. Okay, bye.
Thank you, madam.
Thank you.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you.